Good morning, everyone, for today's distinguished webinar series in AI and cybersecurity. Today's distinguished speaker is Dr. Latifur Khan, Professor, Department of Computer Science, UT Dallas. The title for today's talk is Generative AI, including LLMs for Cybersecurity. Dr. Khan is a tenured full professor at University of Texas, Dallas, where he's been teaching and conducting research since September 2000. He received his PhD degree in computer science from University of Southern California in August 2000. In addition, he received his bachelor degree in computer science and engineering from Bangladesh University of Engineering and Technology. Dr. Khan is a fellow of IEEE, IET, BCS, and ACM Distinguished Scientist. He has received prestigious awards, including the IEEE Technical Achievement Award for Intelligence and Security Informatics, IEEE Big Data Security Award, and IBM Faculty Award in 2016. Dr. Khan has published over 300 papers in premier journals and prestigious conferences. Currently, Dr. Khan's research focuses on big data management and analytics, data mining, and its application to cybersecurity and complex data management, including geospatial data and multimedia data. His research has been supported by grants from NSF, NIH, the Air Force Office of Scientific Research, DOE, NSA, IBM, HPE. Dr. Khan, it's indeed an honor to have you as part of the UND's Distinguished Webinar Series. Thank you so much for taking the time to do this webinar for us. The floor is yours.
Yeah, thank you. Thank you for your nice introduction. You can hear me, right?
Yes, I can hear you. Yes.
Okay.
So typically we do this talk for 45 to 50 minutes and have a reminder 10 minutes of Q&A,
Cool. Okay, so I'll talk about first our...
We cannot see your screen. Do you want to share your screen?
Oh, I thought I shared the screen.
Yeah, you did initially, but I think we went back to introduce you. Sorry about that.
You can see the screen?
Can you make it full screen, please?
Sure. Okay, so
sounds good.
In this work, I will talk about stream mining work first. Then I will talk about generative AI, how it can be used for text processing and cybersecurity domain, that type of thing. Okay, so let me introduce you what is the data stream means. Data stream means data are continuously coming, and you can think about sensor data, network traffic, social media data. These are example of the streaming data. Here in network traffic, we know that packets are continuously coming, and some packets might be benign, some packets might be malicious. So this data can be treated as a streaming data, then sensor network, various IoT devices will be deployed in the environment that produce humongous amount of data, and that can be treated as a streaming data. Then social media, where we post the messages like in Facebook or Twitter, that can be treated as a streaming data. And this streaming data, or data stream mining, is different from the traditional machine learning or traditional data mining. So that I will explain in a minute. So in this work, we focus on the classification problem. So the idea here is that classification is a supervised learning where you need a label data ground to build the model. But we want to address the classification in the setting of stream. And we have some historical data. Using those historical data, we build the model. When the new test data comes, we want to do the prediction. Now, how it is different? It is different because we need to continuously update the machine learning model. And here, why we need to update the model continuously in a stream setting. The reason is, one of the example in cybersecurity is this. Let's say we have some network traffics are coming, and it passes the firewall. When it passes the firewall, there is no guarantee that the traffic will be benign. It can be malicious, So we want to deploy a classification model, and the model will categorize incoming traffic, whether it's a benign or malicious. If it is benign, then it will go to the server. If it is malicious, then we will stop it and do further analysis. Now, the problem is this classification model, let's say we train it in the beginning of the year, then we test this model all the way at the middle of the year and at the end of the year. So now the issue is attacker may not follow the same attack patterns. They may change their attack patterns. So in that case, this model will be obsolete very soon if we do not update the model, because we trained our model at the beginning of the year. Now, let's say we are going to utilize this model for testing purpose at the end of the year. An attacker is always adaptive, and they try to change their attack pattern. So in that case, the model will be very soon will not be able to detect new types of attack and so on. So now the question is, we need to update the model in a stream setting. And which point we'll update? We can update very frequently, like every hour. Then there is an issue also. There are two extremes. We can update the model very frequently, every hour or every minute. But this updating the model requires computing resources. At the same time, it requires training data or ground truth. And training data or ground truth will come from human, which will be costly and subjective. So this solution, if you want to update the frequently, there is a possibility that no update is required, but still you are updating, you are wasting your computing resources and you are wasting your money, and human annotation is always expensive. Other extreme is, why don't you don't update the model or update the model less frequently? So at the end of the year and so on. So then in the middle, model will perform poorly. So there is a trade-off. So we develop some novel technique where we can identify automatically this is the right time to update the model. So the point is, we develop some mechanism that will figure it out automated way that this is the right time to update the model. And then we will ask at that time human to give us the label and so on. So this is our contribution. We made a very good contribution that this is the right time to update the model. How we do it, that I will cover in a few minutes. And this model is very effective to do the zero-day attack detection in cybersecurity. Okay, now what is the challenges for the stream setting? The challenge is characteristics of data may change over time. So let's say we have two-dimensional data points, and these are the positive instance in the training data, and these are the negative instances. And we create a decision boundary like this that will separate positive instance from the negative instance and so on. Now, the decision boundary, so this is the, let's say, first week of training data we have, and we build a model like this. And using this model, we want to do the prediction on the week 2 data. So we will say above this, everything is the negative, below this, everything will be positive. Actually, these blue points will be, now what happened in this week 2 data, the decision boundary is changing. So the old decision boundary is not valid anymore. The new decision boundary will be something like this. So in that case, all of these blue points will be misclassified. So our goal is to identify those blue points correctly. So if we do not update the model will not be able to catch these new types of, will not be able to identify these blue points correctly. So that shows that since the characteristics of data are changing, so we need to update the model. That's the important part here. And then we are the first who handles the concept evaluation or brand new class in the stream. Let's say we have two existing classes, positive class and negative class in the stream, and we build a decision boundary like this. So if the points in this quadrant, it will be positive class. If it falls into this quadrant, it will be negative class, some decision tree. And now some test data comes like this. So we'll identify, in this case, this X. Some of them will be identified as a positive class. Some of them will be identified as a negative class. In fact, this X should form a brand new class or emerging class in the stream. That should not be a part of the positive class, or it should not be a part of the negative class. So you can see here, existing machine learning algorithm will not be able to identify this existing class. It will be identify this novel class as an existing class. It will not be identified this X as a novel class or brand new class or emerging class. So this is the problem with the traditional machine learning. So we develop a technique where we can identify correctly that this bunch of X points will from a brand new class or emerging class in a multi-class setting. So here I will explain this concept evaluation or brand new class or emergent class more clearly. So x-axis represents the timeline, y-axis represents the class. So far up to 400 in the stream, we see class 1, class 2, class 3. And after 400 time unit, novel class instances are emerging. So in this case, class 4 instances, so up to 400 in the stream, we have only class 1, class 2, class 3. And the machine learning algorithm does not have any clue about class 4 instances. But all on a sudden, after 400 time unit, in the stream, we are seeing class 4 instances. So in that case, class 4 instances will be known as a novel class. So now in this stream setting, we want to do the classification problem, and classification requires some label data ground truth to build the model. So there are two phases, training phase and the test phase. So how the test phase works, in this case, we utilize ensemble-based technique. Ensemble means we keep multiple models. So on the ensemble, let's say we have 3 models and test data comes X, we want to do the prediction. Each of the model will come up with a prediction. 2 of them say positive plus, 1 of them say negative plus. We will apply majority voting and make the final decision. And now the question is, first part is the testing. So how we do the training? So for the training, we divide the data into a number of chunks, fixed size chunk. So here, just think about D1, D2, D3. These are the, let's say this is a chunk 1 data. So we have first 1,000 instance will form chunk 2, second 1,000 instance will form second 1,000 instance will form chunk 2, third 1,000 instance will form chunk 3. And so there are, let's say at the beginning, we have 3,000 training data points. So we build 3 models, M1, M2, M3, and ensemble, we keep these 3 models. And now new chunk arrives, and in that chunk, we have all the test data. So 1,000 points, and each of the point will be treated as a test data. We'll do the ensemble will come up with the prediction with the majority ruling. And then time passes, we may have some ground truth. So once we have a ground truth or level data, we'll build a model. New model will be built, M4. So we cannot simply add M4 in the ensemble. In that case, ensemble will grow over time significantly. So what we do, we want to find a replacement for M4. So ensemble has a 3 model, M1, M2, M3. We want to see which one is performing worse on the most recent training chunk. In this case, let's say M1, M2, M3's performance will be determined on the most recent training chunk D4. And we observe that M2 is performing worse in terms of the accuracies or error. In terms of the error, it is highest, or accuracy, it is the lowest. So M2 will be thrown away, M4 will be in. So this way we update the model. And then with updated model, we will do the prediction on the new incoming test chunk and so on. And time passes, this test chunk, we may have some ground truth. We build a model, M5, and now M5 needs to be added in the ensemble by replacing one of the existing models. So M1, M3, M4, these 3 models will be checked against the most recent training chunk, D5, and we observe that M3 has the highest error. So M3 will be thrown away from the ensemble and M5 will be in. So this way we update the model. And this way we are arguing that we can handle the concept drift because we are continuously updating the machine learning model. And now the question is, how do we do the brand new class or emerging class? So here are the steps in details. So here, okay, so here we have some, as we said, when some test data comes in the chunk or stream, we will first this test data, each of this in the chunk test data, whatever we have, each of the model will come up with a prediction. And if all of them say is an outlier, then we will buffer it. And then we will detect the novel class. If some of them say is a part of the existing class, then we will classify it as an existing class and so on. On the other hand, when you have a training data, we build a model, new model will be built, and now we need to find a victim in the ensemble. Basically, in this case, ensemble has a L models, L equal to, let's say, 3. So we need to add the new model by replacing one of the old model from the ensemble. So this way the algorithm works. And our novel class detection has a 3 steps. The first steps works during the training time, and the second step and the third steps are works for the test time. So this first steps actually builds the decision boundary at the finer grain, and then second step try to determine whether it's outlier or not, the test case, and then from there we try to determine whether it's a novel class or not. So let's talk about each of these steps in details. So we create the decision boundary, as I said, at the finer grain. So this is our original training data. And if we build the decision boundary, something like this using decision tree, it will come up with a quadrant like this. And you can see here a lot of unused space. So here the decision boundary is constructed at the coarser grain. It's not tight, it's very loose. So that's why novel class will not be detected correctly. So now what we do, in our case, we create the decision boundary at the finer grain. So let's say we have 1,000 points here and 400 points here, 400 here, 100 here, 100 here. So we will build 100 clusters, 40 here, 40 here, proportionately 10 here, 10 here. So this way we create, for each quadrant, we come up with a bunch of clusters. And the clusters, we keep the clusters, small clusters, cluster centroid. You can apply k-means clustering algorithm. We keep track of the cluster centroid and the radius and other statistical information and so on. And now, instead of keeping this quadrant, in our training data, we keep the small clusters information as during the training time. So we keep track of the cluster centroid, radius, and some other statistical information. We call it this cluster as the pseudo points. And now test data comes. So this way we create the decision boundary at the finite grain. So test data comes, and for the test data, what we do? So now we have a test data. This X is a test data. And this is one of the model we have. And the model has, so we have, keep in mind that we have ensemble has a L number, L equal to 3 models, let's say. So one of the model is like this. So you have a bunch of clusters. And now test data comes. And this is one of the test point X. And this X distance between this cluster centroid and this X actually is smaller than the radius of this cluster. Therefore, this X is part of this cluster. So therefore, X will be known as an existing class. On the other hand, this X is not covered by any of this existing classes clusters. Therefore, X will be known as a raw outlier. And this raw outlier happen due to the novel class or due to the concept drift or due to the noise. So we have to isolate those scenarios. So now, keep in mind, in our model, at the beginning, what we did, we have L number of models, and each model say that this is an arrow outlet, then all of them say arrow outlet, then it will be a filter outlet and is a potential candidate for the novel class. Then we will buffer it. If one of them says not an outlet, then it will be an existing class. Then once we have this filter outlets, bunch of potential novel class, we will see that whether this potential novel class instances a cluster or not among themselves. So the idea here in our case, when the novel class emerges, it will not emerge as a single instance. A bunch of points will be an outlet, and at the same time, those outlet points, they will be close together in the space, and at the same time, they will be far away from the existing clusters. If that's the case, then we call it this filter outlet points will form the brand new class. So for that, we use silhouette coefficient, one of the clustering property. So what we do, we take the filter outlet points, and we will see for each of these points, we calculate the silhouette coefficient. And if we see at least a q number of points have this characteristics, then we call that those as a novel class. Otherwise, it will be known as the existing class. So how I do it? So this slide will explain that more details. So here, you can think about these are the positive class instances. These are negative class instances. And this is the filter outlet by this model. And then this filter outlet points, all these black dots, they're close to each other. And at the same time, they're far away from the positive class, far away from the negative class. Therefore, this will form a brand new class or emerging class. So that we try to capture it using silhouette coefficient. So the work I presented so far has a bunch of problems. The problem is we assume that data is continuously coming, and we divide the data into a fixed chunk. Let's say here k equal to 1,000, first 1,000 instance will form chunk 1, the second 1,000 instance will form chunk 2, and so on. And then we update the model after a certain chunk and so on. But in reality, this might be a problem because problem is, as I told you before, if we set the chunk size too small, then we will frequently update the model. And we may waste the resources. No model update is required, but we are still update the model. Or if we set the chunk size too large, let's say 10,000, and after the first 1,000 instances, the concept drift happen, or brand new class instances are emerged, but still we will wait because our chunk size is 10,000, and after first 1,000 instances, concept drift happen, or brand new class instances are emerging. So then we have to wait additional 9,000 points. After that, we'll update the model. So this is a problematic scenario. So we have to set the chunk size dynamically, and basically we have to determine on the fly this is the right time to update the model. So for that people try to do it using they call it adaptive chunk size or sliding window. So here they monitor the machine learning models error rate, or the classifier or ensemble's error rate. If the error rate goes up in the window, then they will feel that that the model is not performing well. We need to replace the model. But how do you calculate the error rate? In order to calculate the error rate, we need to know the ground truth. And who will provide the ground truth? Human will provide the ground truth. So it's a supervised model to estimate the error rate. But the problem is in the stream that are continuously coming with a very high speed. This is not a realistic scenario. So what we suggested is a little bit different. So instead, our method is not a supervised at all. It is fully unsupervised. It's fully unsupervised. So what we did on the training, the test data are coming. Let's say we have one window window has a n number of points, and at this point, the window grows all the way to n equal to, let's say, 100 points. And when you do the prediction, the model will come up with a prediction. And during the prediction, it comes with, let's say, the first instance belongs to a certain class with a confidence level is C1. Second instance belongs to, second test instance belongs to class 2, class C2, I'm sorry, belongs to a class with the probability confidence value is this. So this way, when you do the prediction for each of the test data, we have some confidence value. So if we see that this confidence value is very high over time in a window, then we are happy with the current model. But if we see that in the window, this confidence value is going down over time, then we feel that the model is not performing well. We need to update the model. So that's why here what we do if we have an n number of points and we see at a certain point where there is a distribution shift happen or not. If there is a distribution shift means a significant change happens, then we will see that we need to update the model. If there is no significant change, then we will simply keep our current model and grow the window size. So that's the very basic idea. And we did experiment on a bunch of data set. First two data set are synthetic data set, and then this is the packet calls, system calls we use. And forest cover, these are the non-security data set, activity detection, movie reviews, and so on. And then you can see these are the number of classes, and these are the instances. And we treat the data as a stream. And our goal is to reduce the false positive rate, false negative rate, error rate, and so on. The results are reported here in terms of the error. Lower the number is better. And so these are a bunch of data set, and you can see the newest work, all of our approach basically. But so these are the fixed chunk size approaches, and this is the more dynamic one. So you can see our approach has a very low false positive. At the same time, they have a very low false negative rate, and error rate is also low. In this case, false negative means novel class instances we identified as existing class, and so on. So this is the first part of my talk. Do you have any questions so far? And no, we claim that it actually very effective to identify the new attacks or novel attacks or zero-day attack. We demonstrate in our experiment.
We can continue to the talk and I can reserve the questions at the end.
Sure. Okay, so the second part of the talk, we focus on the semi-supervised learning to address the imbalance issue of the tabular security data set, and that work was published in a number of conferences and journals. So you know that in cybersecurity setting, most of the cases we may have a benign case, and then few cases we may have a positive class or attack class instance. So this will introduce class imbalance issue, because once you have the training data like this, let's say you have two types of two class problem you're talking about. One is the benign, other one is the attack class. So you have maybe 90% is a benign and 10% is a attack class. If you train your machine learning model, most of the cases machine learning algorithm will identify as a benign and so on. But 90 to 10% are very reasonable ratio. But if it is 99 versus 1%, then the machine learning algorithm will not learn anything, because it's data imbalance issue. There is a majority class and minority class issue. And what we do when you do the experiment, in our case, for security data, we saw there are 5,692 records, and we try to do the vulnerability detection here. And we see 99% are non-vulnerable, and only 1% in these examples are vulnerable case. So you can see here data is extremely imbalanced. And what problem we try to solve? We have a bunch of C functions, and each of the functions we want to determine whether it's a vulnerable or not. So this is one of the vulnerable functions. And for our experiments, so we have a bunch of source code Cs, and then from there we extract some features and generate the feature vectors. So these are some of the features we use for each of the C source function. So we use structure-based features like number of parameters uh, and the number of linearly independent path, number of loops in the functions, number of source lines, number of local variables, then flow-based features, then binary-based features, number of assembly code binary conditions, then the pointer-based features. So these are the features we generated from each function. Basically, we generate a bunch of features like this. So our feature, eventually the function will be represented with a feature vector with a 40 dimensions, say, for example. And for machine learning algorithm, we use various standard machine learning algorithm, XGBoost, multi-layer perceptron, support vector machine. These are standard technique. And then these are all supervised model where you need a level data or ground truth to build a model. Our case, we use semi-supervised learning. What is the difference between semi-supervised and supervised learning? So one of the extreme scenario in machine learning, you need a level data ground truth that is called fully supervised model. And if you don't have any level data ground truth, then it will be unsupervised learning. Clustering is an example of the unsupervised learning. So here we consider the middle ground where we have semi-supervised learning. So the idea here is we have few level data points and a lot of unlabeled data points. And from there, we build a machine learning model. And in real life, we have that type of scenario. So BIME and contrastive mix-up, these are the two semi-supervised learning we have. So how we do the semi-supervised learning in our case? So we have imbalance data set. And let's say we have a minority class. So from the minority class, okay, so there are a bunch of steps here. The first steps for the minority class, we do some data augmentation, and in a machine learning algorithm, especially in the images, this augmentation is very trivial. Just think about you have an image contains cat and dog. You rotate the image, it will create a new image, or you flip some of the pixels, that will create a new image, but still that image will represent cat and dog class level set. So this way, data augmentation for image case is very easy. But in our case, think about, we don't have the image. What we have the bunch of rows or the records. And from there, we want to create a new records. And we want to focus only on the minority class or vulnerable case. Minority class here is vulnerable. So from the vulnerable cases, we want to do the data augmentation. So create additional examples. So what we do in this case, we have our case, the augmentation from the 3 examples, we will create a 4th artificial examples. So let's say xi, xj, xk, these are the 3 records we have. From these 3 records, we will do some weighted. You can simply take the average and create a artificial example x bar. So in this case, this way 4th examples will be created, and this example will be the artificially created. And but this will, since xi, xj, xk all represents vulnerable case, so x bar will be also known as a vulnerable case. So this way, we do some data augmentation. For minority class, we create additional examples. And then from the level data, we build some machine learning model. And in this case, we do some contrastive learning. What is contrastive learning? Contrastive learning means when the instances are contrastive learning means if I have an instance and from there I create an additional instance by flipping, rotating, and so on, or augmentation. And then in the embedded space, we want to learn an embedded space where this original points and then the transform points or augmented points will belong to the same, will be close to each other. They should not be far away. So that is called contrastive learning. So in a supervised case, contrastive learning means if I have two instances, both of them represents a vulnerable case. In the embedded space, these two instances because representing vulnerable case should be close to each other. On the other hand, if I have an instance A that represents vulnerable case and instance B represents non-vulnerable case, in the embedded space, A and B should be far away. That we want to learn in the contrastive learning case. Okay, so once we have some preliminary initial model we built, that initial model now will be used to test for the unlabeled data, and we will generate some of the pseudo labels. Some of the label will be generated from the trained model, and those predicted label will be known as a pseudo label. We don't know the actually ground truth, and using that we will update the machine learning model, and we'll continue, and then that way we'll build the model. And we tested this on a number of data sets. So the first batch, this part represents supervised learning. And again, these are the unsupervised learning. I'm sorry, these are the semi-supervised learning. And so here, no triplet accuracy is very high. You know that data is imbalanced, so all of them will be benign and so on. And but when it comes to the positive rate to detect the vulnerable case, all the supervised learning fails. It cannot detect any of this. And without, since this approach is no data augmentation, so it fails. But when you do the data augmentation for the supervised learning, we observe that still it fails, or it can detect some of them later. But with the semi-supervised learning, with the data augmentation, we observe that it performs well. It performs, basically it outperforms the supervised learning. It can not only detect the benign case, it can also detect the it can not only detect non-vulnerable case, it can also detect the vulnerable case. And then we compare this approach with some of the other data augmentation technique. Smooth is widely used as a data augmentation technique in the past. So we compare it, our approach, and we show that our approach is doing better. And then so that concludes first part of my talk. Let me talk a little bit. I have 5 minutes or 10 minutes.
You can take as long as you want, another 5-10 minutes, depending on.
Okay. Give me 1 minute.
Or if you prefer to end, I can have and ask Q&A sessions, if you want.
You guys are cybersecurity group, right?
Great.
Okay, yeah. No, I'm trying to find more cybersecurity related work.
Meanwhile, folks can put their Q&As as we're about to end the webinar, so folks can put their questions as you based on the presentation.
Okay, so let me tell you a little bit. Okay. Still on the screen. Okay, so this is a little bit old. I think 2 years old work. I couldn't remember that much, but I can tell you a little bit. So we do some federated learning to detect the cyber attack. Federated learning you can think about is a machine learning in a distributed setting. So we have a bunch, and federated learning provides you, because the client or there are a bunch of parties, they don't want to share the data. They can share the machine learning model parameters with the cloud or with the central server, but they don't want to share the raw data and so on. So the idea here is we may have some initial model, and the initial model resides in some cloud and so on. And then those model parameters now will be sent to the client and then the clients will have their own data. So they will update this existing model parameters based on their current data, and then updated parameters will be sent it back to the cloud or the server, and the server will aggregate them and send the updated parameters back to the client again. So this way multiple rounds will be taken place, and after that the algorithm will converge. So this way it will give you better protection, privacy will be preserved, and at the same time security will not be compromised and so on. So here we do federated learning to detect the cyber attacks. So think about the car manufacturer collect their own data independently. This includes uh, this data often includes sensitive information such as CAN ID, making manufacturers reluctant to share it. So centralized machine learning model will not work here due to the privacy concern and so on. So we propose a federated learning approach, and multiple client devices has their own local data and train individual local models, which are then combined. So think about this is a manufacturer one, this is a client one, and this case, just where's the mouse? Okay, so this client. Okay, so manufacturer, think about this manufacturer one is a client one, or let's say this is a Toyota, this is Honda, this is maybe Ford. So each, and we have some of the attack data here. So this case, we have the fuzzing attack, but this case we may have something and different types of attack in the manufacturer one or client one has, and client two may have entirely different types of attack and so on. So now we train the model for each of this attack data we have, and the local model will be prepared and sent to the client, sent to the server, and server will do the aggregation as I told you before. Now, but the problem is here some of the attacks may happen, maybe very may not appear, some of the attacks may appear only in one client or one manufacturer. It may not exist in other manufacturer and so on. So in that case, if I train my own machine learning model like this way, the standard following standard federated learning, it may not work very well. So what we suggest here, we do first triplet mix-up, generate some additional synthetic data. So as I showed you previous work, we have three, let's say, attack instances, X1, X2, X3. From there, we create a fourth example, artificial examples, by simply taking the weighted average and so on. And then this way, additional examples will be created, that we call it synthetic data. And then those synthetic data, we will add additional noise so that the privacy will be preserved, because we are sharing this synthetic data to the client server or to the server. and then the server will have some send some of this data to the client, because the problem is, in our case, as I told you, that some attacks may be prevalent in client 4, but it may not appear in the client 3 at all. So client 3 may not have that data about particular attack that resides in client 4. So by creating this synthetic data, we are going to share those synthetic data across other clients and so on. So that way, we will create, we are arguing that when we create these additional examples, we add some noise and then we share it. So that way, we are achieving better performance in terms of the accuracy, and also we try to not give a better protection in terms of the privacy. So that type of thing we did. And then the last one I'm going to talk about in how the generative AI, especially large language model, can be applied in the various cybersecurity problem and various transportation related problem. So here you can think about, this is more in the, we have a bunch of transportation related documents we have online. So this documents talks about, this is one of the diagram that talks about the transit security. So these are the two entities, and then there is the information flow between these two entities. So this information flow, we want to link it with the MITRE technique. You know that MITRE technique has a knowledge base where that talks about various attacks and then the protection or the defense. And the NIST also maintains some of this attack, and they describe, and then they also provide some of the, basically in their case, they call it control. And they also provide some of the defense mechanism. So our goal, given this diagram where we have a bunch of these are the entities that talks about, say, some of the transit security information. So here, each of this box actually has some textual description. Then this one has also textual description and so on. So our goal is to map this to MITRE technique, basically link it with the MITRE technique. Now the question is, this information flow, we call it, we need to link it with the MITRE technique. And recall that MITRE technique maintains a knowledge base. And in that knowledge base, they have a bunch of tactic, and under tactic, they have a bunch of technique. And each technique that describes, they have some textual descriptions. So our goal is to map this information flow into a MITRE technique. So this mapping will be done through the how much this description shares or links or shares with the MITRE technique description. MITRE technique certain, MITRE certain technique description, it may overlap in terms of the textual similarity. Then we can say that probably this one matches well with that particular technique. So for that, we are this textual similarity, we're going to rely on the large language model. And you know that large language model, or which is a transformer-based language model, is a generative AI. It also sometimes it hallucinates a lot. So because it hallucinates a lot because it may not have enough knowledge, or it has a tendency always to produce answers. Even if it doesn't know, it will try to give you the answers. So we try to address that issue using called Retrieval-Augmented Generation model. So in this case, we give a context. So this is my context. Give me the answer from this context. So that's the retrieval part. First will identify from the context a relevant segments, and then those, basically RAG has two components, retrieval part and the generator part. Retrieval part will come up with the appropriate segments, and then those segments will be fed into the generator model, means the large language model, and large language model will come up with the answers. And in this case, we observe that this way, actually, large language model drops the hallucination problem some extent. And in our work, we not only rely on the RAG, we also rely on the we also considers the multimodal data. Keep in mind that in our case, this transit security diagram has not only text, it has some diagram like this. It has also some images and so on. So instead of the textual LLM, we rely on the multimodal data and so on. So we use a multimodal LLM for this purpose, and we show that when you use the images and the diagrams for that along with the text, actually the performance improves some extent. And we also consider these are the LLM is more, you can think about as a more prompt-based technique, one shot, few shot type of learning utilized here. But we also do some supervised model where we do the BERT model. BERT will give us the embedding, and then we treat the problem as a classification problem. And actually, BERT model performs better than this LLM-driven approach. BERT is also LLM, but is more encoder-based model. And okay, so I have some. Okay, so I want to stop here. And then the last but not least, we did some work we have some vulnerability detection database. We link it with the MITRE technique and so on based on the large language model and supervised model and those type of things.
Thank you. Thank you for your presentation. So I think we'll open up for questions session, and let's see. Okay, so let me start with the first question. From part one of the talk, could you elaborate on the methodology used to classify a new data point as an outlier? What specific model or technique are you employing for this classification?
Yeah, very good question. So new data point as an outlier. So when the new data point comes, first we try to determine whether it is covered by any of the clusters or not. Cluster is a part of the training. From the training data, we build the cluster, as I told you. And the cluster contains the centroid and the radius information. Now, if a test data is a part of any of these existing clusters, then we identify it as a it will be labeled as existing class and so on. And then we identify which class it belongs to. It will not be treated as an outlier. On the other hand, if a test point is not covered by any of these clusters, then we call it the raw outlier. Then from the raw outlier, we buffer it, and we further check whether these outlier points are close to each other or not. And at the same time, they should be far away from the existing classes clusters. If that's the case, then we call it as a novel class.
You mentioned that training data is labeled. However, in the case of streaming data, how do you determine whether an incoming instance is benign or malicious, given the absence of predefined labels? Given the absence of predefined labels.
Yeah, so
Yeah.
at the beginning, we assume that we have some, because it's a supervised model, at the beginning, we assume that we have some ground truth to build the model initially. And then we will start to test it on the incoming test data. And then time passes, because over time, let's say after 1 month, you may provide some additional new training data. So then using those new training data, we will update the model. So during the test time, we don't need any level data. We just do the prediction, come up with the class level, predicted class level. Some cases it might be correct, some cases it might be wrong. And for our case, if it is a novel class or zero-day attack, we will just say that this might be a potential candidate for the novel class, but we will not be able to tell you that this is a attack number 5. We cannot come up with the class level. For that, we have to assume we assume that some expert, security expert, will provide the class level later. But in our case, at least we can say correctly that this might be a brand new class or emerging class that the machine learning model doesn't have any clue. But standard machine learning algorithm will always identify the novel class as an existing class.
Super, thank you. We have another question. You talked about zero-day attack. In your work, did you specifically look at particular type of attack of detection? Can you shed some light on what specific attack that you guys have focused on, the zero-day attack?
So for our case, I remember we used, give me 1 minute. I think the one of the data set I showed you that has
Denial of service or some kind of other.
right.
This is the
Yeah,
question.
just think about this. Let's say for our experiment, what we did, let's say we have 5 attack class and 1 benign class instances we have. So in the stream, we may train first benign and attack 1 class and build the model. And then in the stream attack, we have a benign class, attack 1 class, but also all on a sudden attack 2 class instances are coming. So you can think about, yeah, so let's say fuzzing attack is not part of the stream so far, but all on a sudden fuzzing attack is instances are coming. So in that case, our goal is to identify fuzzing attack as a novel class and so on. So, and then when we identify this is a novel class, then human will give the label, then it will be part of the existing class, and time passes, new attack may emerge, so that new attack may be known as we call it zero-day attack, and so on. And our goal is to detect that type of novel attack effectively.
Thank you. What are the techniques used to generate synthetic data? This is another question.
I think there are some stream generator tool available online. At that time, we use from New Zealand, there is a MOA framework, MOA. So they generate a lot of synthetic data. So using that, you can create the synthetic data and then utilize, and the stream setting utilize it. And for a security domain, basically some of the data set may have timestamp. Based on the timestamp, we organize it as a stream. You can argue that may not be always correct way to do it, but since as long as if the data has a temporal or timestamp, temporal aspect or timestamp, then you treat them as a stream data and organize it that way.
Great. You know that for a continuous streaming data, concept drift problem has been there for a while, and what do you recommend for readers who are listening to you right now in terms of adaptive windowing method? Of course, you shared some methods that you talked about in your work that is decades old, but in recent work, how do you see, the challenges in handling these?
Yeah, that's a very good question. So basically in this work, I did not talk about deep learning. So when you do the deep learning and a stream setting or continuous learning setting, we observe that catastrophic forgetting happens. So and let's say you train your machine learning model with some task, and the some task, let's say you identify cats and dogs in the images. And then let's say a machine learning or deep learning algorithm goes here to detect the image image level. And then time flies, new task arrives in the stream. You want to now identify from the images positive sentiment, negative sentiment, neutral, or basically you want to identify happy face or sad face in the images. So this is a new task. And now what will happen? Deep learning case, you will fine tune your model for the sad class and the happy class instances and so on. And now when you test it, the images containing happy class or the sad class, it will do very well. But if you at that point in task 2, if you try to identify the images contain cat or dog, which is a part of the task 1, for the task at the task 2, the model may not perform well to identify the cat class and the dog class and so on. So this is what we call it catastrophic forgetting. So it is well trained on the most recent task, but it may starts to forget the old task. So for that, people try to address that issue. And one option is you can keep some of the old samples, and when you fine tuning it, you will utilize those old samples also. So that way, as a more instance based, the forgetting will happen less. There are another ways is keep some of the old parameters frozen so that model will not be changed that much. So we did some work actually, and then we have a paper in EMNLP to address this issue, catastrophic forgetting. So I should talk about that. Yeah, so
Sure.
that's a very interesting area to explore.
Thank you, Dr. Khan, for your time this morning. I think I'm looking at the time. I think we're almost done with my time, but I think I appreciate for you taking the time to do the webinar for us. I think you will receive a nice plaque from UND and a nice letter from our dean of thanking your time. So hopefully we can continue our collaboration and some proposals, and I'll be chatting with you offline and getting back to you and see
Yeah, let me know.
if we can do something. Thank you, Dr. Khan.
Thank you. Bye-bye.